I would like to thank the organizers for giving me an opportunity to present my work here, which is titled Probing the First Galaxies with JWST, a work that I'm carrying out with my supervisor, Tirthankar Roy Chaudhary. So essentially, a few years ago, with the launch of the James Webb Space Telescope, has ushered in a revolution in the field of extragalactic astronomy, enabling us to look deeper and further back in time, particularly during the first billion years of cosmic evolution since the Big Bang. And this has been accompanied by detections of a large number of galaxies at redshifts of greater than 10. And this entire endeavor has not been without its own share of surprises. The first set of surprise that came in when the early results were coming in was the fact that JWST had been detecting a large number density of very massive and UV bright galaxies at redshift greater than 10, which was in odds with the expectations from traditional galaxy formation models calibrated to pre-JWST results. Here is a plot of the luminosity function, essentially the abundance as a function of luminosity, and these are some spectroscopic constraints, lower limits from the surveys and the bunch of theoretical models, and you can see that bulk of them were below these limits. Only the ones which were calibrated after the early results came in are consistent. And there was a pretty huge body of work in order to understand these results, and they came in two flavors, cosmological and astrophysical in nature. And I will not go into the details of them, but whatever be your solution to this issue, there are also implications of those solutions that you would like to believe, particularly given the fact that there are concurrent large-scale effects from galaxies, particularly regarding the ionization of the intergalactic medium, since we believe that the galaxies and the radiation from them drove this process. So therefore, any constraints on the properties of galaxies would immediately translate to our understanding of the progress and the timing of reionization. And a second subtle factor that comes in is the fact that along with the radiation from galaxies contributing to ionization, they would also heat up the intergalactic medium, and this rise in temperature sets in a UV background that feedbacks onto the galactic processes, particularly star formation within low mass halos, suppressing their star formation rate and quenching them, thereby having a rich interplay between the process of galaxy formation and evolution with the progress of reionization. To leverage these things, we tried to build a self-consistently coupled analytical model, starting from the dark matter halo properties, and our goal was to estimate the statistical properties of galaxies and their large-scale impact. And this is usually framed in the language of finding a galaxy halo connection, which demands that we understand how to populate galaxies within dark matter halos, and we do this in an analytical setting. Which involves finding out the star formation rate associated with the halo in which that particular galaxy resides, and these involves modeling the star formation efficiency, the time scale, the availability of gas within that particular halo. And as I mentioned, that as reionization progresses, the availability of gas within galaxies which are formed in already ionized regions is expected to be impacted due to radiative feedback, and we account for that by this kind of a functional form which is centered around a critical mass scale which is affected by radiative feedback, and this only impacts galaxies which are forming in already ionized regions. And using this star formation rate, it is rather straightforward to compute the luminosity of the galaxy and also the ionizing emissivity from the galaxy, which involves modeling the intrinsic production rate in terms of the star formation rate, and using a light to mass ratio to get the UV luminosity, and also the fact that not all ionizing photons that are produced by a galaxy will leak into the intergalactic medium. And we solve this entire chain of things in a self-consistent manner to get a handle on the observables. So essentially our approach involves modeling these processes, and we have 9 free parameters in our model that model the UV radiation production as a function of mass and redshift, the escape fraction of ionizing photons as a function of its mass, and a free parameter that takes into account the effects of radiative feedback towards the end of reionization, and we fit our model simultaneously to the luminosity function data and the reionization observables to get a handle on these parameters. So here I am showing the comparison with the data. These are UV luminosity function plots at 9 different redshifts from our model. And what we find from this exercise is the fact that the UV emission is required to be higher at high redshifts in order to match the JWST results. This is what these two plots show, basically the normalization and the power loss slope of this relation. And this can be interpreted through either having a larger efficiency of star formation, or star formation happening very quickly in bursty phases, or a different nature of stellar population altogether, which would keep the same star formation rate, but give you a higher yield of UV luminosity. But the luminosity function is rather blunt in the sense that these appear in a degenerate combination, and it is very difficult to disentangle, which is the primary reason behind them. Before moving on, we also check with the consistency with the reionization observables, and we find that our models prefer faint galaxy-driven reionization, where the low mass galaxies tend to show higher Lyman continuum escape fractions, which is quantified through these constraints. However, a check for the models or whether we have been able to pin down the galaxy halo connection using only luminosity functions requires us to move to higher order statistics, typically 2-point statistics like clustering, which is quantified through the galaxy bias. And we can do that in our model, since if we assume a particular model of the halo bias and knowing how galaxies populate halos. And here I am showing the respective predictions from our models for 2 different observation studies. We use the same cuts as done in those particular studies, and when we compare with the data, what we find is that these are the brighter galaxy samples, and we are able to reproduce their measurements without any further tuning of our model. However, for the fainter class of galaxies, what we find is that at low redshift we tend to overestimate the bias, and reconciling the bias measurements would require us to push these galaxies into low mass halos so that their galaxy bias predicted from a model is lower and in agreement with the measurement. However, there is a consequence into which we run into as soon as we try to do this, because low mass halos in our hierarchical structure formation are more abundant. So at these redshifts, if you try to push galaxies at fixed luminosity into low mass halos, you will end up overproducing their abundances. And this plot essentially shows that if you want to if you try to reproduce the galaxy bias and reionization observables, what we end up facing is a surplus of UV galaxies at these very redshifts, where we are matching the galaxy bias measurements. And therefore, there seems to be a tension between the different data sets, and this is promising in the sense that these would enable us to pin down the galaxy halo connection much more precisely. To reconcile these different measurements under a unified framework, what we did is we took the resort of the concept of a duty cycle. Essentially what it means is that we assume that not all galaxies at a given redshift is observable to us in the UV. And our assumption that goes in is that only halos that have recently formed can host a UV detectable galaxy, and this definition of recently formation is one where we tie it to the star formation time scale. And using the duty cycle prescription of 20, we show here, we calculate the duty cycle, which is inherently mass dependent as well as redshift dependent. So here I am showing that the duty cycle for different values of our time interval increases towards massive halos at a fixed redshift, and also increases if you allow more time for fresh halos or mass to be assembled. And as a function of redshift, what we see is that this entire setup translates forward, right? Because we expect halos to have higher assembly or assemble faster at high redshifts. And using this entire machinery, we proceed, this has already built-in characteristics of the fact that if you assume shorter star formation time scales, naturally the galaxies will be brighter, but since a smaller time scale means a smaller duty cycle, they would also not be, the probability of picking them up would be equally lower, representing this stochasticity of UV emission that is typical of high redshift galaxies. And the additional advantage of extending the model using a duty cycle framework is that we are able to break some of the degeneracies. And using this extended model, we redo the entire analysis of trying to match all this 3 set of observations under a single setup. These are the comparisons with the UV luminosity functions, and we are able to reasonably reproduce them. On the left, I'm showing the comparison with the reionization observables. We reproduce them and also continue to find that low mass galaxies are the dominant contributors. And on the right, I'm showing the comparisons with the galaxy bias, and particularly for the fainter galaxies, we are finding better agreement than our original model. Essentially, what this implies is, we find as a consequence is that that the star formation efficiency is needed to increase, as we already found from our only UV and LF analysis. But what we found new from including the clustering measurement is the fact that the star formation time scale requires redshift evolution, where it is low at high redshift, and representing the fact that the galaxies are more bursty at high redshift, and at a fixed redshift, galaxies hosted within low mass halos are more burstier than massive halos. But from this analysis, what we have also been able to find is break this degeneracy, and individually there are consequences or implications from the analysis. For example, the UV luminosity function has given us a constraint on this combined product and as well as a handle on the star formation time scale. Here we quantify the evolution of the specific star formation rate as a function of redshift. If for 2 different galaxies, for example, one with -21, which is the brighter class of galaxies, and an intermediate class of galaxies, compared it with the bunch of individual measurements, and we are in reasonable agreement with the measurements here, although a refined analysis would be required since these points are not taken into account, these particular cuts. Secondly, what we can do is the fact that if we assume a value of a typical light to mass ratio, we are able to extract out the star formation efficiency needed, and that translates to predictions for the galaxy stellar mass function. And here we show predictions from our model and measurements from JWST data, and what we find is that we are able to reasonably reproduce the stellar mass function measurements available at present reasonably well from our framework. And therefore, to conclude, what I would like to emphasize is the fact that using a very simple analytical model that couples reionization and galaxy evolution, we have been able to explain a number of observables from JWST that has given us an insight into the astrophysical properties of these high redshift galaxies, and more importantly, what we have been able to demonstrate that including higher order statistics helps in breaking degeneracies in the galaxy halo connection that are remaining if we only use 1-point statistics like the galaxy UV luminosity function. And with more data, probably our models will be put to stringent tests in the JWST era. Thank you.
No, I have a comment first and probably a question later. The comment is that it is nice that you thought about comparing stellar mass distribution with your prediction, but I simply warn you, because stellar mass is a derived quantity,
yes.
So that is derived under particular assumption of SFH,
yes.
star formation history.
Yes.
So I think you should be careful, otherwise you do the spectral slope versus luminosity. So that will be the better way of doing, because that is what is being used for it. Second point, this question is, you are using large scale bias. What is the scale at which this thing is computed?
So this is a ratio of the correlation function amplitude at 8 megaparsec H inverse by the sigma 8. So at those
8 megaparsec.
Yeah.
Can some changes to the primordial spectrum or non-Gaussianities help you resolve these issues? We thought of it.
Yeah, there have been, I think, some studies in the literature trying to address these issues. So I'm not entirely sure whether it will be able to solve the consistent, reproduce the consistent evolution of the UV luminosity function from 6 to up to 13. What studies have done is that they have usually focused only above 10 and not taken a wholesome analysis.
Yeah, so just quickly, just to clarify, so you find that you just how you resolve the clustering and the abundance issue is that you find that if you populate galaxies which have had a fast star formation in the recent history, then you can reduce the abundance, and also the clustering is correct because you
Essentially, we use the duty cycle. The duty cycle is phrased in terms of how recent there has been an episode of mass change.
Right.
What we do is essentially push them to low masses, but kill the abundance using a duty cycle.
using the
So-
duty cycle. And this comes out naturally from the
Yes.
accretion histories, or
Yes,
you,
yes.
okay, or do you?
No, we use a model where the duty cycle is
Okay, sure.
quantified in these language.
In terms of that. The other question I had is you also make predictions for low mass galaxies at say redshift 0, right? If I wanted to look at like, the satellites of Milky Way or something, and their
We would not recommend that because our analysis is restricted to redshifts above 6. So for example, probably this curve itself, if you pull down, maybe you will start seeing that there are issues. So
okay, but in
We have
principle,
been-
there's nothing.
yeah, then nothing stops us, but
from-
maybe retuning the analysis using some maybe AGN feedbacks will become relevant at solo redshifts.
Right, because
So-
there are reionization, say, quenching constraints from Milky Way satellites and stuff also.
Yeah, but we have not tried them at the moment. So our analysis is restricted above 5 or 6, roughly.
Hi, Ivan. Thank you for the nice talk. I have a naive question. You showed many plots, so maybe I missed it. So there's also an upper limit on the UV luminosity between redshift 25 and 30 by some
Yeah.
photometric observations. Do you
Yeah.
start?
No, we have not used them
You have not.
because
That's
we want.
pretty new, I think.
Yeah, yeah, we have
Okay.
not used them.
But in principle, your model should be. I mean, you can.
Yeah, we
extend
can
it,
check whether we are consistent
With that upper
with that upper limit or not.
right? Yeah. Okay. Okay. Thank you very much.
Yeah.
Yeah, so a couple of things. So did you consider reddening? You have not considered that?
No, we use an effective F star, which has a mass dependence. So implicitly, the behavior of reddening will be captured in the mass dependence of F star.
Mass dependent of F star.
Yes.
Okay. And you also mentioned the IMF variation that,
Yeah, we assume the traditional salpeter thing.
but you have not varied that.
No, because it is absolutely degenerate with this combination. So while we were trying to check this stellar mass function, we kept it as a free parameter, which will try to tune from salpeter to whatever IMF these people assume. So what Anand was saying. So this thing will be fixed that way. In the model, it's just one number that enters.